Hello and welcome back. In this video we will talk about optimization. We will focus in particular on convex optimization, which is we will focus actually on a class of benign problems, of easier problems. If you remember in the previous video lecture, we said that in optimal control we are dealing with optimization problems. If you see here, there is this word minimize. This is what we will try to make sense of today. We will try to define what it means when we say that we want to minimize a function, and we will discuss what it means to talk about when we talk about solutions of optimization problems. So let's get started. I will start with some very easy definitions, some almost obvious definitions, but still I think it is necessary to make sure that we have a very good understanding of everything. So imagine you have the real line of numbers, you have the line of real numbers, and you have an interval. Take, for example, the interval from 1 to, let's say, 3. The closed interval that contains also numbers 1 and 3 are inside this set. And let's give this a name. Let's call this A. I will say that the number A underlined, like this one down here, is a lower bound of the set A if this number A underlined is less than or equal all the elements of A. If this number A underlined is less than or equal all of these numbers inside the set from 1 to 3. So if you take A underlined to be equal to 0, for instance, it is clear it is a lower bound because 0 is less than or equal 3, less than or equal 2.9, 1.6, and so on. All of these numbers, it is also less than or equal 1. This is called a lower bound. Easy as that. Of course, a set doesn't have a unique lower bound. This particular set, doesn't have only a single lower bound because 0 is a lower bound, 0.5 is a lower bound, 0.9 is a lower bound. There are many, or there might be none. A few examples. So this number 1 is a lower bound to the set from 1 to 2. Of course it is. This is the real line. This is the set from 1 to 2. And take this point A underlined to be equal to 1. Isn't 1 less than or equal all of the numbers between 1 and 2? It is. If you are concerned about the left limit, 1 is less than or equal 1. So it's not a problem. 1 is less than or equal 1.3, 1 is less than or equal, and so on and so forth, less than or equal 2. 1 is indeed a lower bound of the set from 1 to 2. But for the same set from 1 to 2, for this set, there are more lower bounds. 0 is another lower bound, minus 1 is another lower bound, minus 5,000 is another lower bound. There are sets that have no lower bounds. This one, for instance, the set from minus infinity to 0. This has no lower bounds. Don't say that minus infinity is a lower bound, because a lower bound must be a real number. Minus infinity is not a real number. Now, given there is a special lower bound I want us to talk about, this is the so-called infimum. There is something special about the infimum. I'll give you two examples. This is example 1, example 2. So in example 1, take the set from 0 to 1. And let's take a few lower bounds. I'll zoom in here. So minus 10 is a lower bound. Minus 1 is a lower bound. Minus 0.001 is another lower bound. So I'm asking how much high can I go? What is the highest lower bound I can choose? And I can indeed go up to 0. 0 is indeed the lower bound, and 0 is less than or equal A for all members A of the set from 0 to 1. And this is as high as I can go. I cannot go higher. 0.1 is not a lower bound, for instance. This is the highest among all possible lower bounds. Now let me give you another example. Take the set from 0 to 1, but this time the limits are open, so 0 is not an element of the set. Then again, minus 10 is a lower bound, minus 1 is a lower bound, so on and so forth. How close can I go to the set? Can I go up to 0? Yes, of course I can go up to 0. That's fine, because 0 is less than or equal A for all members of the set from 0 to 1. So in both cases, both here and here, the highest possible lower bound is 0, although we are talking about different sets. Let me read out the definition for you. It says, given a set A, a set of real numbers, a lower bound A star is the infimum. We call it the infimum. It's a Latin word, the infimum of A. If this A star is above all lower bounds A underlined, for all lower bounds A underlined. The infimum of A is denoted by inf of A. So in these two cases, the infimum of the set from 0 to 1 is 0. The infimum of the set from 0 to 1, not including the limits, is again 0. That's what the infimum is. And yeah, we just gave an example. There are cases where the infimum is inside the set. There are cases where the infimum is not inside the set. This is what we have here. So this 0 here is inside the set. This 0 is a member of the set. 0 belongs to A. In the second example, 0 is not inside my set. 0 is not inside my set. So the infimum may be inside the set or not inside the set. In the first case only, we say that the minimum of the set from 0 to 1 is equal to 0. In other words, you can call the infimum a minimum. In the second case, on the right hand side, here, there is no minimum. You cannot call this infimum the minimum. It is just the infimum. So this is the difference between an infimum and a minimum. A minimum is inside the set, like here. This set, in this case, the infimum is not a member of the set. 0 is not inside this interval. Simple as that, really. Next, say we have a function f that takes a vector and gives me a number. You can think of this as a cost function. So say that this is the set of vectors Rn, and this is the line of numbers. What this function does is that it takes a vector and gives me a number. And let's say now that I have a certain set x inside here. Think of this set big X as a set of constraints. So I'm focusing my attention only to this set big X. So what I'll do now is that I will take this point from inside X and I will see what is the value f of this point, f of x. Let's say it ends up here. I'm taking another point, it ends up here. I'm taking another point, it's here. Taking another point, it's here. And I will continue to do that. And I will see that if I keep doing that, this set, this whole set is mapped to, say, an interval. This one. And let me give you some values. Let's say that it is mapped to the interval from 1 to 10. This interval from 1 to 10. This is the image of the set big X via the function f. So what happens once again is that I am taking a point little x from this set and f sends it to f of x which is a number, and I'm telling you that this number is always between 1 and 10. I use the notation f of big X. What is f of big X? F of big X is a set, first of all. It's a set. We see curly brackets here. This means set. The set of all values of f, f of x, the set of all f of x, where x is taken from inside the set x. And this set f of x is a subset of R. For instance, it can be the interval from 1 to 10, as in this example. Okay, so this is just notation. Since this is an interval from 1 to 10, I can talk about the infimum of this interval, the infimum of f of x, and if the infimum is inside the set, it is inside the set in this case, it is 1, because I said the closed interval from 1 to 10. So in this case, I can say, I don't want to call it an infimum, let's call it a minimum. Okay. Sometimes we use a different notation. Instead of writing the infimum of f of x, we write the infimum of f of little x, where x belongs to the set big X. But once again, don't forget, this f of big X is what? It is a subset of R. For example, it may look like this, from 0 to 1. For example, it may look like this, from 0 to 10. For example, it may look like this, from 0 to 1 and union from 2 to 3. But it's something of this sort. It's a set of numbers. And as a set of numbers, this is the infimum of a set of numbers. Right. Next, if this infimum is attained, I can say I don't want to call it an infimum, I will call it a minimum. So we can talk about the minimum of f of x, which we also can denote like this, the minimum of f of little x, of the variable x, where x is taking values inside the set big X. This notation, infimum of f of x, x is in x, and this notation, minimum of f of x, x is in x, are of course closely related to one another, and they are very frequently used. This is an optimization problem now. It is a problem, first of all. The problem of minimizing f of x. F is my cost function, x is the decision variable, this is what I need to determine. This function f is a function that takes values on a set, from a set big X, and sends them to the real numbers, so it gives me a cost for every vector. This is called the cost function. The set x, big X, is a set of vectors. It is called the set of constraints. A point inside this set big X, so let me do a little sketch for you again. This is the set of all vectors, and this is the real line. My function f maps vectors x to numbers, f of x. It assigns a cost value to different vectors. And I can have here a set x, big X, of constraints. So this is telling me actually you must be inside here. This is a requirement. It's a hard requirement. You cannot violate it. If you take a point inside this set big X, if you take this point little x, it is called a feasible point. The word feasible implies that maybe this is not the best thing you can do. Maybe there is another point here, x prime, a different point, that gives you a smaller cost, like this f of x prime, can be smaller, but it's at least feasible. It's not the best thing you can do maybe, but it's okay, you can be inside there. In pathological cases, really, this set big X can be empty. In this case, we say that the problem is infeasible. Our problems should not be infeasible. And there is the case where X is Rn. This is telling you actually that you can go anywhere you like. There are no limitations, no constraints whatsoever. And such problems are called unconstrained. You have no constraints. So if this is the case, if x is Rn, the problem is unconstrained. Otherwise, of course, needless to say, it is called constrained. So these are just some definitions around optimization problems. Again, we are focusing on this optimization problem. Give me a second. The objective here, what we're looking for, is to determine the optimal value of f over this set x. So we are looking for the infimum of this function f, the lowest possible, the highest of all possible lower bounds, the infimum. This is what we're looking for. This here is what we're looking for. And if we are lucky enough and we can replace the infimum by a minimum, so to put it differently, in different words, if the minimum is attained, then, you know what? Then we can determine a specific point x star. There might be many. This doesn't mean that there is only a single, a unique one, such that f star is equal to f at some point x star. I think it's best if I give you an example. I have a few later. I'll give you one now. Say that my function f of x looks like this. This is x, this is f of x. Then what is the, say that you have some constraints, that x is from this point A to this point B. So this is your function f, and x must be constrained inside the set from A to B. Here I'm taking, for simplicity, I'm taking x, little x, to be a number, not a vector, just a number. What is the set f of big X? It is this. F of big X, this set here. And what is the infimum of that set? I will zoom in now. What is the infimum of this set? It is this value over here. It is the smallest value that my function gives me. Is this attained? Yes, it is attained because the set is like this here. It contains the value. This means that there is a certain x. I will denote it by x star, as in the best x. There is a point x star that gives me this value. And this best value of my function, I will call f star. What is f star? Once again, f star is the infimum of my function f of x, where x satisfies the constraints. And what is this point x star? This point x star is on the horizontal axis. It is of course between A and B, and corresponds to the best value, the infimum of my cost function. I'll give you another example. So suppose that the function looks like this now, like this. Simple as that. And x must be between here, point A, and here, point B. So now this is f of x. X again is from A to B. This is f of big X. It's a closed set again. I'll give you an example later where the set is not closed. So now it is a closed set. It contains its limits, so to speak. So this point down here is my f star. This is the lowest cost that corresponds indeed to, in this case, in this sketch, it corresponds to A. So x star is equal to A. A is the best point. If you want to have the cost corresponding to its infimum, then you have to pick this point x star. So f of x star, the cost of x star, this is the cost of x star, is equal to the best possible, the infimum of all possible costs. So this is what we mean when we say f star, infimum of costs, x star, best point. I'll give you one more example actually, This is x, this is f of x. And say now that your function looks like this. So x is from a to b, x is a number again. This is my f of big X. These are all the possible values of my cost function. These are all the possible values my cost function can take. What is the smallest value? This one here. And this corresponds, sorry, I did a bad sketch, I'll fix it. This corresponds not just to one value, but to many values. So if you choose, give me a second. If you choose this x star, that works. This x star is fine, it works. It corresponds to the minimum value. If you choose, if you move your x star to another place, like here, it is still a good point because it corresponds to the same cost function. So you see there is a plateau here. There is a flat region. All of these points, all of them, correspond to the same cost value. And all of them are called, wait for it, minimizers. So you have here many minimizers. Here you have a single minimizer. Here you have a single minimizer again. This is your minimizer. And this is called the optimal value of the function. So some vocabulary, some necessary vocabulary. Optimal value is the smallest value of your cost function, or the infimum of your cost function, to be more precise. A minimizer is this point if it exists. And yes, there are cases where it doesn't exist. I'll give you some examples where we don't have a minimizer despite the fact that we have an optimal value. There are some cases like this. Now, a point x star, as we said, is called a minimizer. Let's give the definition. The point x star, a point x star is called a minimizer over the set x if this inequality holds over x. So this says that the cost of any x is above or equal f of x star. F of x star is the optimal value. The optimal value. As we said before, this is denoted as f star. It can't get better. That's what this is saying. You cannot find another x that gives you a smaller cost value. If you take any other point, if you take any point x, which is inside x, if you sample from big X, it is impossible, this inequality is saying, to find a point that gives you a smaller cost. The cost that you will be getting from other points will be either the same or higher. So this is the very meaning of optimality, the very meaning of x star being a minimizer over f. And the set now of all minimizers, because there might be many, is denoted like this, argmin. We say argmin is the set of all possible values x star. Because if we go back to this example here, you see that in this example we have many minimizers. In fact, all this set, I'm highlighting down here, all of these points, all of them are minimizers. This is precisely the set of minimizers, argmin of f. We denote it like this, argmin of f, the set of all minimizers. Now, In principle, optimization problems are hard to solve. They are difficult problems to solve. If x is empty, we say that the problem is infeasible. It should not be empty, of course, otherwise the problem doesn't make sense. If f is unbounded from below on x, we say that the problem is unbounded. Let me give you a little example here. So let's say that this is my f of x. Say that x must be between 5 and 6. And let's say that my function looks like this. Here it goes down to minus infinity. This is an unbounded function. So you see, actually, in fact, let's say that, can I give you a better example? I can give you another example, a second example. Say that you have f of x to be a super simple function. F of x is equal to x, and there are no constraints. So the function looks like this. And if you choose x, let's say you do a test, you choose x to be minus 1. What is the cost? Minus 1. Can you do better? Yes. X is equal to minus 2. What is the cost? It's lower. It is minus 2. So this is a better point. If you go minus 3, minus 4, minus 5, if you go all the more, if you move more and more to the left of your x-axis, if you go towards minus infinity, you will be getting lower and lower and lower costs. This function is unbounded because you can always decrease the cost significantly, actually. And not only that, it's not only that you can decrease the cost forever, is that what is f of big X if big X is R? It is equal to R. It is equal to the real line. And the real line, the real numbers, have no lower bounds. F of x has no lower bounds. F of x, f of big X, has no infimum. This is an unbounded problem that doesn't have an infimum. And an optimization problem, of course, may have multiple minimizers. And the simplest case is f of x is equal to, let's say, 123, or whatever you would like to put there. It is a constant function. It is just constant. Whatever point you take on the x-axis, it corresponds to exactly the same cost function. It's like the cost function doesn't care what x you give it. It gives you always, you have to pay always the same fee regardless of the x that you choose. In that case, you have many minimizers. Every choice you make is a minimum in a way. And there is a special case of optimization problems. We stated here that optimization problems are in general hard to solve. There is a special case that might make things easier to work with. The case where x, big X, and f are convex. So the case of convexity, the assumption of convexity, can make our analysis simpler. So from now on, we will be focusing on convex sets x and convex functions f. And you guessed right, I must tell you what convex means. So this is what we will do next. Just a moment. I'll give you the definition, I'll give you the mathematical definition, but actually convexity is something extremely geometric. So I'll read this out for a moment and then we'll focus here to actually understand what convexity means. But let's get this out of the way. A set big X, a set of vectors, is called convex if whenever I take 2 points inside the set X and I choose a number lambda between 0 and 1, lambda x1 plus 1 minus lambda x2 is inside X. Just a little moment. This means that if I choose lambda equals 0.1, 0.1 x1 plus 0.9 x2 is again contained inside X. And if I replace 0.1 by 10%, and if I replace 0.9 by 90%. This is a little more understandable because it says that if you take a point that is between x1 and x2, this is again inside x. So these points here, the points lambda x1 plus 1 minus lambda x2, define what? The line segment that connects x1 and x2. You can think of it as an interval between x1 and x2, although x1 and x2 are really points in space. So this is x1, this is x2, and this line, this light blue line, is the interval between these two. And you see that this blue line is inside this set x, say this is set x. This blue line is inside the set for whatever points I choose. I mean, take this point x1, I'll take a different one, and this point x2. Alright? The line segment is inside, the whole line segment is inside the set big X. Or take, I don't know, take this point x1 and this point x2. The line segment is contained inside x, it doesn't go outside of it. How can it go outside? How does it look when it goes outside of x? It looks like this. If this is your set x, if this is your x now, and it has something like an indentation, a dent actually, if it has something like a dent, then this region is not inside x, it is outside of it. So this is not a convex set, or as we say, it is a non-convex set, one word. So this is a convex set. Some other convex sets are the whole Rn. Just one single point, x0, just the point, is convex. A ball of a norm. How does the ball of a norm look like? When it comes to the Euclidean norm, a ball looks like this. What is the ball of a Euclidean norm? The ball of a Euclidean norm is the set of points x in Rn, the set of all points that have a norm less than or equal r is the radius. So this is a ball. Balls are always convex. This is a ball. In fact, it's called the Euclidean ball. But even if you take a different norm, if you take norm 1, if you take norm infinity, if you take this norm with a matrix Q that is symmetric, positive, definite, then what you will get is again a convex set. Balls are convex sets. Then you have this type of set that is convex. It is called a half space. A half space geometrically looks like this. It is, oops, I'm in the middle. This is a half space. So in 2 dimensions, draw a line and take all the points on one side of a line. In 2 dimensions, take a plane and take all points on one side of this fence, of this plane. And polyhedra are, sorry, I skipped hyperplanes. Hyperplanes are convex. So in 2 dimensions, a line, a single line is a convex set. In 3 dimensions, a 2-dimensional plane, a plane, is a convex set. And polyhedra are convex sets. Okay, I don't want to say too much about these, but these are sets that look like these. Like this, like, imagine like polygons in 2 dimensions. So these are examples of convex sets. Okay, we said what a convex set is. Now, what is a convex function? The definition here is slightly different, but yes, let me read out the definition first of all. Now, let big X be a set, be a convex set. We know what a convex set is already. Now, a function is said to be convex. What is a convex function now? A function is convex if the function at a point of the line segment that connects x1 and x2 is less than or equal lambda times f of x1 plus 1 minus lambda times f of x2. Despite the lengthy definition, this is an extremely geometric definition. I mean, you can look at the function and you can tell whether it is convex or not. I mean, the function we have here is a convex function. Let's see why. If I take 2 points, if I take the points x1 and x2, and I take the value of the function at this point here in the middle that connects x1 and x2, then the value of the function, so what is that here? This is f of lambda x1 plus 1 minus lambda x2. This is less than or equal this point up here, the point on the line that connects x1 and x2. So once again, let me clear this. If you take any 2 points on the line, like this one and this one, and you connect them with a line segment, you take 2 points on the graph of the function and you connect them with a line segment, then the line segment is above the graph of the function in between these 2 points. Or the graph is below the line segment. The graph of the function is below the line segment. This is what a convex function looks like. This is x squared. Have a look at this. This is the absolute value of x. Take a point here and a point here. Connect them with a line segment, then the function is below the line segment. Of course, this doesn't have to be specific to 2 particular points. Take any points. Take, for instance, this one and this one. Connect them with a line segment. Again, the line segment is above the function. The function is below the line segment. Or take this one, the exponential of minus x. Take any 2 points on the function, any points you like this one and this one. The function is below the line segment. Now, as a counter example, this is not a convex function. This is x cubed, x to the power 3. It is not a convex function because if you take this point and you connect them with a line, it is not true that this line is above the graph of your function. I mean, it is here, it is up here, the line segment is below. Here the line segment is above. But for sure it is not true that the line segment is above, because here, you see here, it is below. So this is not a convex function. We need to ask the following question. Okay, let's say you give me a function. How can I tell whether the function you give me is convex? So this is the question we will address afterwards. So how can I tell whether a given function is convex? And one might say, what do you mean, how can I tell? I will use the definition. I will take this inequality and I will check whether it is true. Well, yes, okay, you can do that theoretically, but in most cases it is not very convenient. In most cases you have to put quite some effort to use the definition to tell whether a function is convex or not. And there are significantly easier ways to do that. To talk about these easier ways, to talk about convexity criteria, we need to look at the derivatives of this function. But we have functions that take vectors and give numbers. So derivatives have been defined. I mean, you're familiar already with derivatives of functions f from R to R that take a number and give a number. We have now to generalize this definition to functions that take vectors and give numbers. The first thing we need to do is to define the partial derivative. with respect to just one of the variables. I'm stating the definition here, but mainly what I'm trying to say, despite the formula here, is that this is all about a derivative with respect to one of the variables only. So say, I think it's better for me to give you an example. Say that you have a function f that takes a two-dimensional vector and gives a number. Let me give you an example of such a function. It can be the function f of x, and x is a two-dimensional vector, we said, is x1 squared plus x2 squared. So I'm giving here the definition of the derivative of f with respect to either x1 or x2. Let's do the derivative of f with respect to x1. This is called the partial derivative, like this. The partial derivative only with respect to x1. So x2 is a constant when I'm differentiating with respect to x1. I'm ignoring x2 entirely. So this is 2x1. That's it. The derivative of f with respect to x2, now I'm ignoring x1. x2 is the only variable I have. This is 2x2. These are my partial derivatives. And this is the definition if you want to have a look. It's not a very complicated derivative. It looks really like the standard derivative of a function of one variable, but it is not x plus h. It is x plus h times this vector ei, and this vector ei is a vector that has zeros everywhere, and it becomes active, so to speak. It wakes up and takes into account only the ith coordinate. But the bottom line is, what happened here, x2, the bottom line is that this is how it works. This is how partial differentiation works. And we ended up here with two derivatives, not just one. So this function has two partial derivatives with respect to x1 and with respect to x2. Okay, and if you take these partial derivatives and you put them in a vector, I'll keep talking about this particular function. If you take the derivative with respect to x1 and the derivative with respect to x2, yes, and you put them in a vector, what you have defined here is the gradient, like an upside down delta. This is the gradient of your function f, and this gradient is a function of x. Let's look a little closer. What is this really? It's a function that takes a vector and returns what? Another vector. It takes a vector and it gives me a vector. This is called, once again, the gradient of f. The gradient of f at a point x is denoted like this, and it is a vector. Pay attention here. I have put one next to each other, and then I'm putting a transpose here. The only reason why I'm doing that is because I didn't want to have an expression that was vertical. It wasn't convenient to present it on the slide. That's why I have the transpose here, so I can write the expression horizontally. So this is the vector of all partial derivatives of my function f. Now, if f is differentiable and this derivative is continuous, we say that f is continuously differentiable. So this is just a term you will hear me using often. So the term continuously differentiable means two things. Means differentiable, the function is differentiable, and this quantity here, the gradient of my function, is a continuous function. Now, second order differentiability is an extension of what we just discussed about. It is really the following thing. Say that we have a function f that is continuously differentiable. It is differentiable and the derivative is continuous. It is a function like the one we studied before. It takes a vector, gives me back a number. We can talk about second order partial derivatives like this. I think it's best again if I give you an example. Take f of x. X is a two-dimensional vector. Take it to be x1 squared plus x2, let's say to the power 4. And I want to determine, let's say, the derivative of f, the second derivative of f, with respect to x1. This is the second derivative of f with respect to x1, which is what it is the derivative with respect to x1 of the derivative of f with respect to x1. I'm treating x2 here. When I say derivative with respect to x1, I am treating x2 as a constant. So what do I get from here? I get 2x1. So what is the derivative of that with respect to x1? And this is equal to 2. So the second derivative is the derivative of the derivative, which is the derivative of 2x1, which is equal to 2. Let me give you another example. What is the derivative of f, the second derivative of f, with respect to x1 and then x2, x2 and then x1 actually. This is derivative with respect to x1 of derivative with respect to x2 of f, which is derivative with respect to x1 of, now I want you to differentiate this function with respect to x2 and ignore x1. x1 is a constant. So it is 4x2 to the power 3. 4x2 to the power 3. Now, this quantity, I want it to be differentiated with respect to x1, but there is no x1 here. So the result is 0. And long story short, this function has 4 second order partial derivatives, these ones. Second order derivative with respect to x1 squared, second order derivative with respect to x1 and then x2, sorry, x2 and then x1, second order derivative with respect to x1 and then x2, and second order derivative with respect to x2. We have 4 such derivatives. However, good news, these two are equal to one another, provided they are continuous. And these 4 thingies, these 4 functions, if I put them in a matrix, this defines the so-called Hessian of F. So check this out now. F is a function that takes a vector, gives a number. The gradient is a function. The gradient is a function that takes a vector and gives me a vector. I'm not sure why the pointer doesn't work. I'm having a technical problem, but this is a function that takes a vector and gives a vector, the gradient, and the Hessian is a function, this thing here, the Hessian is a function that takes a vector and gives me a matrix. A matrix that contains what? All possible second order derivatives of my function, namely the derivative of f with respect to x1, x1 and x2, and so on, x2, x1 and xn. And then the same, up to the derivative, the second derivative of x with respect to xn. And likewise, we can talk about twice continuously differentiable functions. Also, if all second order partial derivatives exist and my Hessian function is continuous, then we say that f is twice continuously differentiable. Also, in that case, the Hessian is a symmetric matrix. It's a matrix. The Hessian is a matrix. The gradient is a vector. The Hessian is a matrix. Why are we discussing about these things? How can the gradient and the Hessian help me tell whether my function is convex? It's very simple, really. Have a look at this function over here, this function. This function is convex. If and only if I can do the following thing. Take a point, take the tangent, and then the function is above the tangent. Take this point, take the tangent line, the function is above the tangent. It must be above the tangent. What is the tangent of the function? It is this. This is the tangent line of the function f at the point x. So the function at any other point, y, let's say, is above the tangent line of the function at x. So once again, take a point, this point, take the point x, take the tangent line, which is this line here. Now the pointer works all of a sudden, that's very good. And you see that my function, the graph of my function, is above the tangent line. This is the geometric understanding of how this criterion works. The tangent line now, to define the tangent line, I need the gradient of f. So the tangent of f at a point y is equal to f of x plus the gradient of f at x transpose times y minus x. This is the tangent of f at x, determined at x, at a point y. So this is a point y. Sorry, this is a point y here. This is the tangent line. So this is criterion number 1. This is how differentiability, and namely the gradient of f, this is how the differentiability of f helps me tell whether f is a convex function. I don't want to give you too many examples now because you'll come to class and we'll discuss there. And this is a nice figure where I have simply taken different points, I have sketched the tangent lines, and we can see that the graph of the function is really lying above all of these tangent lines. This is one way to tell whether your function is convex. And there is another way, I think this is perhaps the most convenient criterion. Determine the Hessian. We said that the Hessian is a matrix. It's a matrix, in fact it is symmetric. And check whether the Hessian is positive semi-definite. If it is positive semi-definite, then the function is convex. Of course, the function has to have a Hessian. It has to be twice continuously differentiable. Example. Take a quadratic function. F of x, I'll write it again, is 1/2 x transpose qx plus q transpose x. First of all, determine the gradient. Determine the gradient of this function, which is, now I want you to pay close attention to that because this is the most significant and important identity that we will be using all the time throughout this module. What is the gradient of 1/2 x transpose qx? If q is a symmetric matrix, then this is simply q times x. And I want you to keep paying attention to what I'll say now. What is the gradient of q transpose times x? The gradient of this fellow is simply little q. That's it really. This is the gradient of f. And lastly, what is the Hessian of f? The Hessian of f is simply the matrix q. There you go. It's this matrix q. So is this q positive semi-definite? If q is positive semi-definite, then the function is convex. So you can tell whether a quadratic function is convex by looking just at this matrix q. If q is positive definite, then your quadratic function is convex. Right. So what is next? Sorry, let me see how much more is left here. I don't think we can do the whole of it, but let me just tell you a couple of more things just to conclude this section. Say now that you have an unconstrained problem, which is the simplest case of an optimization problem. I have no constraints. I want to minimize a function and I don't have any constraints. Actually, let me ask you something else. Let's say that you have a function f. You know this from high school, certainly. You have a function f of x, and this is a function that takes a number. X is a number, not a vector, just a number. And now you want to determine the minimum of that function. What do? I suppose you know Fermat's theorem, or you might not know it by this name, but I'm sure that the first thing that will come to your mind will be to take the derivative of that function and set it equal to 0. So maybe, if you do that, maybe you will find the minimum or a minimum of this function. You might not, however, I suppose you know that as well, you might not find the minimum because your function might look like this. In which case you will find a maximum if you set the derivative equal to 0. But you know what? You might find something that is neither a minimum or a maximum because your function may look like this. X to the power 3 looks like this. So in that case, if you set your derivative equal to 0, you will end up at this point, which is not a minimum, it is not a maximum. Okay, it feels like it's a pity this doesn't work. However, we can certainly tell something about the cases where we have a minimum. So say we have a minimum x star. Let's say even we know that this x star is a minimum. If you know that it is a minimum, then what must happen is that the derivative of this function at x star must be equal to 0. This is called an optimality condition. It is a condition that the minimum must satisfy. It doesn't mean that if you solve the optimality condition you will find a minimum. You might, or you might not, or you might not. But if you have a minimum, then certainly it satisfies this condition. Of course, I didn't mention it explicitly, but this function f has to be continuously differentiable. It has to be differentiable, and in fact it has to be continuously differentiable. If a point x bar, like this one, x star in this case, satisfies this condition, then it is called a stationary point. When you hear the phrase stationary point, I want you to think that this is a possible, perhaps think of it as a candidate minimizer. It may be a minimizer, it may not be a minimizer, we'll have to check. It's a stationary point. It's better than nothing in a way. So determine a stationary point if you can, and then we'll see. You might be lucky and you might have actually found a minimizer. But this is at least one thing you can always do. You can start by stating the optimality conditions of the problem. This is known as an optimality condition, something that a minimizer must satisfy. Now have a look. Let x star be a minimizer. It is a minimizer. If it's a minimizer, then it is also a stationary point. This is true. Minimizers are stationary points. I'm talking about functions that are continuously differentiable functions. All minimizers are stationary points. The converse is not true. Not all stationary points are minimizers. In general, not all stationary points are minimizers. If, however, and this is the beautiful news, this is the breaking news of the day, if f is convex, then all stationary points are minimizers. You know what this means? It means that it now suffices to solve this equation. If you want to solve this problem, if you want to solve the problem minimize f of x, it suffices that you determine a stationary point. If f is convex, then all stationary points are minimizers. This is super convenient and super useful. Of course, it holds if your function is convex. If it is not convex, unfortunately, it's not true. and let me state this here, I have put it in a box. If f is a convex function and it is continuously differentiable, then the set of all stationary points is equal to the set of all minimizers. The stationary points are minimizers. The minimizers are anyway always stationary points. In other words, a point x star is a minimizer of f if and only if it is a stationary point. Stationary point, the notion of stationarity becomes identical to the notion of being a minimizer. And this video ended up being slightly longer than I expected, but nevertheless I think it's worth concluding with an example. Take this minimization problem, our old friend the quadratic function. Suppose that q is positive semi-definite, so that this is convex. This function here is convex, because we said that quadratic functions are convex if and only if q is positive semi-definite. I've written that here. Actually, we know that this is convex. Therefore, all stationary points are minimizers. Okay? It's not too difficult now. This is what characterizes stationary points. We need to solve this equation, right? We need to solve this equation over here. We know what the gradient is. It is big Q times x plus little q. We need to solve this equation. So now solve this equation if you can. And if you can, you have determined a minimizer. Well, can you solve this equation? Can you do this really? I mean, I don't know. Can you do this? And then say that x star is equal to minus q inverse times q. Well, you can do that only if you know that q is non-singular. Is q non-singular? The answer is not necessarily. So what can you do? This is one of the reasons why we did all this introduction on linear algebra to make sense of linear systems. So I'm going now to erase this because it's not true in general. We don't know whether q is invertible, whether q is non-singular. This is a linear equation. This is what I want you to keep. This is a linear equation. So if you want to make sense of this as a linear equation, we're looking for x star, go back to the videos we did on linear algebra, and hopefully all the answers to your questions will be there. So for now, I think we should stop here. We'll put a full stop. And there is still a little more we need to discuss about optimization problems. Like, for example, how do we know in principle whether an optimization problem has a solution at all? We are actually very close to concluding the chapter on optimization, and then, using what we did here today, we will solve lots of examples and we'll move on to optimal control. So we'll put this theory to practice so that we can actually solve optimal control problems, and we will start with the simplest form of optimal control problems that we are, as I said, we're able to solve on paper, and these are the linear quadratic optimal control problems. This is actually one of the reasons why we discussed about quadratic functions here again and again, because we will be using quadratic functions. So that's it for now. Thank you very much for watching, and I'll see you again next time. Goodbye.